Okay, so I'm recording. Welcome, everybody. This is 3031 Thermodynamics and Statistical Physics. This is me, Sui, and my detail is here. You can find me in my office 304, although most likely you are not here in the campus, but we are still business as usual mostly. So if you have anything you want to discuss with me, you can always make an appointment, and I can receive you in my office. If you prefer to reach me by email, this is my email, and I will try my best to respond. I cannot guarantee an instant response, but I will try my best. Okay, and we can also set up a Zoom meeting. Okay, so just a little bit of introduction about me. I'm an experimental solid-state physicist, and this is some of the pictures from my research. So basically, my group works on materials. The materials that shows interesting properties, for example, superconductivity, magnetism, or some interesting transport properties, such as very large resistance when you apply magnetic field, and so on. And in the research group, we are mainly using diamond to create pressure. And in this course, thermodynamics, you will see pressure a lot, right? You will talk about pressure, you talk about volume, and this is a very typical system to discuss thermodynamics. So this is actually something which is nice to keep in mind. What you are discussing here in the course can actually have very relevant real-life application, at least application in the research world. So here, how do we create those pressure? How do we change the pressure? How do we use pressure as a way to understand the materials? And this is this schematic diagram in the middle kind of give you some idea. So basically, we have some materials of interest that we put in the middle of two very hard materials. So here we need to use diamonds to do this, and we squeeze it, and basically this is the concept. If you can put your material in between very hard materials, so here is diamond, you can actually reach very high pressure. But the point here is creating pressure is not really that difficult, but to really study it, to be able to study the material under pressure is something else. So this is what students of my groups are very good at doing. So they are able to extract information under pressure. So how do you study this guy when he's surrounded by all these materials? So surrounded by metals, surrounded by diamond. Okay. Another thing, another concept that you will meet a lot in this course is heat capacities. So we will develop a lot of thermodynamic properties. And how do you know these thermodynamic properties are correct? You need to do some measurements. Sometimes some measurements are not easy to do. And for example, you will meet the concept of entropy, which is a very important and very subtle and very mysterious concept in thermodynamics. And how do you deal with entropy? How do you measure entropy? How do you understand entropy? How do you have some feeling about entropy? So here you will learn how to manipulate partial derivatives. So you will be able to get some measurable quantity that relate to entropy. Okay, so this is kind of the logic behind this. How do we know what we are developing here is correct? So we need to do some measurement, and some of the most intuitive measurements we can do in the lab is heat capacity. Okay, so this is some of the data shown here, and you see you can clearly see some anomaly here. Otherwise, you have a very smooth background. Look at this black one, right? So this is all related to this course. Okay, another thing you will learn is the phase diagram. So phase diagram basically tell you how to reach some interesting phases. For this course, most likely you will talk about the pressure volume phase diagram. And this is something kind of familiar to you. For example, when you discuss water, the water can go through different phases when you change the temperature. And what happens to the volume, what happens to the pressure when you undergo different phase transformation. So that kind of information are captured in the phase diagram. For our research, we are talking about some different kind of phase diagram. So we usually plot our temperature along the vertical axis. And we like to travel along the horizontal axis by pressure, right? That's why this diagram is here. We like to apply pressure and see what happens when we kill some phase transition temperature. And this point here is called a critical point, but this is not the usual critical point we face every day. This is a special type of critical point, which we call the quantum critical point. And my group is interested in studying what happens around this quantum critical point. Can you, for example, make the superconductivity around the quantum critical point? Can you optimize it? Can you enhance the property of the superconductor? And so on. Okay, so this is some relationship between this course and the previous courses. Sorry, what happened to the? Sorry, do you see the on my screen some? Can you still see the screen? Can you still see the slide? Okay. Somehow on my screen some words didn't show up, but now do you see the full screen? Do you see some funny words missing? Is it okay? Okay, so if there's no complaint, it should be okay. Now this course, what is the relationship between this course and other courses? So hopefully everyone here has taken 2041. So this is University Physics 3, and you cover a lot of materials. In particular, the kinetic theory of gases would be very important for this course. So there, we are not going to redo everything, but at least the concepts you develop there will be relevant to us. Then we have the laws of thermodynamics covered there. And this is something we will do it again, start from the first law, start from the 0th law, and then work our way through to build all these laws of thermodynamics again. And the aim here is to be able to do some statistical mechanics later for the second part of this course, and hoping that we can link these two parts of the course. Okay, another course that is relevant to this course is 4031, Statistical Mechanics. So some students actually skip my course and jump directly to 4031. And this course, you will do a lot of ensemble theory, and you will talk about interaction. And that is not the purpose of this course. So here we are not going to talk about ensemble. We are not going to talk about different ensembles. We're only going to pick one ensemble and try to get as much result as possible. And we are going to talk about weakly interacting particles. Okay, so 3031 kind of sandwich between these two courses. And so logically, it will be better, in my opinion, to take it according to this sequence. So 2041, 3031, 4031. But I've seen students taking 2041, 4031, and then they come back to take 3031. That is also fine with me. Okay, so of course, some of the materials will look a little bit, the logic will be a bit different in that case. Okay, so here as I already mentioned, we want to develop thermodynamics more formally. And then we are going to cover additional topics, such as thermodynamic potentials, phase transition, the third law. And we are going to use the language of statistical physics to understand the behavior of a large number of particles. So here, the key word is large number. Okay, non-interacting, we should think about it as weakly interacting, but very weak, such that we can ignore the detail of the interaction. But we need the notion of interaction, even though it's very weak, to establish thermal equilibrium. Okay, so in this course, this is what I'm going to cover. According to the teaching syllabus, this is what we aim for. Okay, so we are going to spend roughly about 2/3 of the course on here. Okay, this year, we somehow term 2 of this year is a bit short. Usually it's 13 weeks, but this term is only 12 weeks. So we will have to work a little bit harder to cover these materials. Okay, so I would like to warn you a little bit, because this is a material you have seen, some of the material you have seen, but maybe less formally. So I'm going to go a little bit faster. And then I want to reserve time, roughly the same amount of time, 1/3 of the course, to discuss statistical physics. Okay, so here we are going to give the microscopic interpretation of entropy. And this part is very fun, but it really requires you to have some solid knowledge of thermodynamics. We are going to, when we are here, we are going to switch back and forth and try to have a logical presentation. Then we are going to talk about some very important concepts, distribution functions, Fermi-Dirac, Bose-Einstein, and the Maxwell-Boltzmann, which Maxwell-Boltzmann is something you might have seen before. Then we are going to learn how to count. So the concept of density of states will be important. And after that, we are going to apply everything we learn here, up to here, density of states, to try to get some physics out. Okay, we are going to talk about the ideal Fermi gas and the ideal Bose gas. Okay, the recommended textbooks are given here. When I prepare for this course, I read all these books. Okay, I take bits and pieces from these. And the first one is the Equilibrium Thermodynamics by Atkins. This is a famous textbook, kind of the classic in the field. A little bit old, but really it's a classic in this field. And these two, the other two, are newer. So the second book by Blundell and Blundell covers both thermodynamics and statistical mechanics. So this is a little bit, the thermodynamic part is good for us. The statistical physics part is a little bit too much. Okay, so but it's still useful to use it as a reference. Another one which is newer is this book by Steen. This is a rather thick book, about 200 pages, and almost entirely on thermodynamics. So this book has a more modern flavor, and is also a rather nice reference. This book has more words, so you need to be patient to read. So if you want to get equations quickly, then this book you might find it a little bit too long. Okay, but anyway, these are the books. They are luckily all available through CUHK library. You can download the entire books basically, so don't have to buy. Okay, the website of the course is this. This website contains all the standard information. For example, the key dates, the assessment scheme, recommended textbook, TA's details, my detail. Okay, I will provide a full set of notes, and this year I'm doing something new to me. I have never done it before, but this year I'm going to put all the notes on Blackboard. I used to host everything using the departmental website, but now I want to try something new. Okay, and the videos will be will be uploaded to Panopto. I would, well, my aim, I will see how it goes. I will try to give videos, but if it's not necessary, we will stop doing that. Okay, but if videos are needed, they will be hosted here. Okay, so a little bit of warning. So some of you have taken my lectures before and you know my style. So in the class, I like to write. So you will see me writing a lot of things, and I will sometimes, kind of depending on my mood, I might give you more stories, and those are not in the lecture notes. Okay, so you are supposed to read the lecture notes and you are supposed to come to the lectures. Okay, so that is, and more importantly, I will be very happy to receive feedback. I want to interact with you. In particular, in this kind of environment, the only way I can interact with you is if you cooperate with me. Okay, I would talk about this more. Okay, the assignment and the assignments and exercise classes questions will be downloaded, can be downloaded from the course website, actually from Blackboard. Okay, so I'm going to put everything there as well. And you are also going to submit your assignments through Blackboard. Okay. Okay, my consultation hours is Monday, 5 to 6. I also accept email appointments. I will be grateful if you give me some notice. Don't just write me an email and say, hey, I'm around, I'm eating lunch. Can I see you in 15 minutes? This is usually not okay for me because usually I need to work based on my calendar, unless something really urgent comes up. Okay, the TA of the course, Zhang Wei, who is actually here. Wen Yan, I think, is also here. Both of them are here. If you want to, maybe later, maybe you can see their faces later. And then Hui may be here, maybe not. Let me see. Okay, maybe not here. Okay, so the consultation hours are listed here. These are the consultation hours, and you are welcome to approach them during the consultation hours. So I have asked them to monitor their email closely during the consultation hour. So you can write to them and ask for the Zoom meeting, for example, and they are requested to react to this. Okay, important information, but standard. Okay, homework. This is an assessment scheme. Homework will take 20%, midterm will take 30%, final will take 50%. And please let me remind you that in order to qualify to be assessed for this course, you need to achieve at least 20% in all written exams. Otherwise, even if you achieve 20% full mark in the homework, if you fail to achieve 20% in the written exam, according to the criteria referencings, this is an automatic F. Okay, so be careful. Exercise class will start on week 2. So this week, no exercise class. Actually, exercise classes, we have 3 slots a week. Surely you will be able to find one that suits you. And the first problem set will be announced at the end of this week or early next week. You will usually be given about a week to deal with the problem set or the assignment. Okay, so the first problem set, the deadline of that is Monday, 2 weeks from now. Okay, so that is after the airdrop period. I don't want to collect the problem assignments and then later find out after spending all the time to mark, you drop the course. So that is not very fun for us. Okay, so we will collect your assignment by 11 a.m. 25th of January. Okay, and usually for my course, the assignment deadline is strict, which means it's a step function. If you don't hand in, you get 0 immediately. Okay, so again, please, this is a third-year course. We should learn to be well organized. If you have problem, if you want some more time, you need to write to me earlier. You don't write to me 5 minutes before the deadline. Okay, another thing which is important, and please mark it down right away, is the midterm. The midterm will be on the 10th of March, which is a Wednesday on week 8. Okay, and this is the lecture hours. And that, unless you have very special reason, otherwise missing the midterm will also automatically result in a 0% in this component. Okay, now let me share a little bit of insights on how to have a successful or enjoyable experience for this course. So first, you need to show respect for this course. So in the past, this is the third time I teach this course. For the past 2 sets, I really had a very enjoyable interaction with the class. Okay, so I'm sure we can do it again here, given the challenge I will list out soon. Okay, and you need to be willing to put in effort to attend lectures and to take assignments and exercise classes seriously. Okay, these are designed to help you learn. So the assignments questions are designed to complement my lecture. So they are designed to help you learn. So the more effort you put in to handle this yourself, the more you will achieve. Okay, so here, because of all this online teaching, unfortunately, I do not see you anymore. So sometimes I do not really know when somebody send me an email saying that you're a student of 3031, I do not really know your real identity. So please, if you want to contact me or contact us, please use your CU Link account. And likewise, when I send anything official, please pay attention. This is very dangerous if you don't. Somebody can pretend to be me and send you an email saying that midterm is cancelled. Okay, so, but be careful. Unless the email is sent from my CU Link mailbox, you must not take those as official. So let me put it this way, all of my official announcement will be sent through my CU account. Okay, and this is the third term we are doing the online teaching. We have learned a lot. Everybody has learned a lot, and you should try your best to optimize your learning environment. So for example, a good screen would be helpful. A good headphone will help you. And then I request you to have some papers ready next to you, so you can do some calculations. Because you will see very soon, sometimes I will ask you to do some calculations. I cannot see whether you are doing this, but take this chance to have a a small break from looking at the screen. At least you can look at the paper, write something, do some calculation, and this is also nice for everybody. Okay, and you will see this from time to time. And finally, if you are very good at Zoom, please do not mess up my teaching. So for example, if you use some functions that disturb me or your classmate, that is not fun. So please don't do that. Okay, finally, very quickly, we don't like people copying homework. And if you do, we know about this. Okay, so for example, this student A, student B, even the grammar mistakes are the same. Don't tell me we cannot tell. Okay, and something like this, when it happens, usually the easiest way is just to give the names of the 2 students directly to the faculty office. And we will try to not to bother with this anymore. And if we receive something like this, this is our approach too. We will just collect all this, and you will be dealing with the disciplinary committee of the faculty yourself. And let me say that if you copy your friend's homework, if your friend is doing it by himself or herself, actually both names will be submitted. So you might actually lose a friend this way. So be careful. Okay, so that is all about the ground rule. And I will stop sharing and take question if you have any. Do you have any question? Everything clear? Okay, questions. Were students taken 431 last sem have a great advantage in this course? Now, I have a few students taking this course before. I think based on the final grade, I would say they're kind of scattered around. Okay, so I wouldn't say it's great advantage, but certainly some of the materials I've developed here might look a little bit more familiar to them. Are you one of them? Okay, yeah, more question, Miss. Sorry, I cannot tell whether it's Mr. or Miss. Okay, student Lee, you raised the hand, right? Ah, you raised the hand because you took the course. Maybe that's the meaning. Okay, then we will see whether you have some advantage. Right? So, yeah, but it's too late now. Everybody knows you took the course. No, I'm only joking. All right. Any more? Okay, if not, let's start the lecture. Okay, let me give me a bit of time, a few seconds, and take this chance to take a break. I'm going to set up my whiteboard. Okay, I guess you can see. Can you see the whiteboard? Sorry. What am I sharing now? Okay, this is what I want to share. Okay, do you see my writing? Say okay, guys? Okay. All right, so now I do rely on your feedback, okay? So if you don't mind, just raise your hand or do the thumb up or whatever, just kind of important. I don't want to spend all the time writing and then suddenly you say, I cannot see you writing. Okay, so let's begin from the thermodynamics part. Okay, so what do we do? Why do we need thermodynamics? The reason is we want to understand the properties of material or the matter in thermal equilibrium. So for this course, we are mainly talking about equilibrium thermodynamics. Okay, so we want to look at, we want to investigate, we want to look at the property of material at thermal equilibrium. Okay, so important keyword, property, we want to, properties of matter at thermal equilibrium. Sorry. Okay, so obviously here you have a different approach. For example, if you are building a bridge, you want to know the thermal expansion coefficient of steel. You want to know about your steel, and you want to, more importantly, if you are an engineer, if you are doing this work, you want to be able to correct for the change of length, the change of size. So that will have something to do with the thermodynamic property. Okay, for example, thermal expansion is one of the properties we care about in this course. Okay, how do you do this? So you have different approach. One approach is look at the macroscopic property. For example, what I just say, macroscopy. So this is an A here. Okay, macroscopic properties include, for example, what is this material? This material can be copper, can be steel, can be iron, can be whatever. So first you talk about the material. And then how do you study this material? You can measure the length, you can measure the volume, you can change the temperature, you can repeat and look at the same property again. Of course, the material still will not change, but the volume can change, the length can change. Okay, so these are all macroscopic properties, right? So you look at the length, you look at the volume, and you look at the response of this when you change the temperature. Okay, so temperature. So this is a macroscopic thermodynamic approach. So this is the this is governed by thermodynamic. Okay, and you can also look at things differently. At this point, as a third-year student, this is not surprising to you anymore. You can you can discuss the motions of the atoms, right? The microscopic approach, you want to look at the atomic details. You talk about atomic energies, you talk about the motions of atoms, you talk about electrons, you talk about all these microscopic details. Okay, so you talk about these and electrons maybe. And then you discuss what happens when you inject some thermal energy, what happens to all these particles. So this is another approach, but this is of course very difficult because if you take a piece of steel, you will have a lot of particles. Okay, so this is a difficult thing. The difficulty here is you have many particles, roughly 10 to the 23 particles. If you take a piece of a lump of steel. Okay, so for this approach, you need to know you need to learn how to deal with large numbers. And that is when you find statistics helpful. Okay, so with the help of statistics, you can do statistical physics. Okay, statistical physics will give you a way to try to have a bridge between this very detailed description of the microscopic details and the thermodynamics property you see when you look at the same piece of material. Okay, so this would require statistical physics. Okay, so here we can also talk a little bit about the different states. So using the same term, we can define something called a macro state. Again, this is a macro state. Okay, so these are the states or the variables you see when you talk about macroscopic properties. So this is the variables associated with macroscopic properties. And likewise, the microstates will be the variables associated with the microscopic properties. How do you describe all these atoms? How do you describe all these electrons? So you will have a way to describe them. And this kind of details will be encoded in the microstates. Okay, so for example, you learn the kinetic theory of gases. And you know, if you want to if you take a sample of gas, you have a lot of gas particles. If you really want to describe this volume of gas, you need to specify a lot of quantities, a lot of parameters. For example, if you have one particle, you can associate this particle, the positions and the momentum of that particle. Okay, so let's take an example. So example, in the kinetic theory of gases, kinetic theory, when you describe one particle, you give 6 coordinates, right? So for each particle, so for each particle, you talk about the positions. You can talk about positions and the momentum in all 3 directions. So you need to give the momenta. Okay, so if your particles are moving in the 3-dimensional space, you have 3 coordinates from here and then 3 from here. So altogether you have 6 parameters for each particle. And if you have n particles, you have a very long list, and this will give you a lot of parameters to deal with. Okay, this will give you 6n parameters. Okay, so how do we move forward? How do we move forward to get something from here, from the microscopic theory to the macroscopic observable, and that is our aim towards the end of this course. Okay, so we need to start from the thermodynamics, and then we will slowly move on to the statistical physics, and then we are going to come back to look at some of the thermodynamics again. Okay, so to give you some example about this microscopic and macroscopic pictures. Now, a very good example is the following. Let's take this class. We have how many students? So for this class, let's say I told you we have about 56 students. Okay, what are the microstates and what are the macrostates? Okay, we can take this example and use, for example, the midterm score as an example. So if I want to analyze the midterm score of this class in the most detailed possible way, so what I will do in the microstates picture, what I will do is to list out all these coordinates for each student, right? So if I use the midterm score as an example, what I will simply do is I would write student A, and I write the score. So for example, student A, 10% only, sorry. And then student B, and then I can keep moving. This is student get 95% in the midterm. Okay, this is very detailed. This is like statistical physics. When you have all these microstates to deal with. For each particle, you list all the details possible. Okay, and so on. Okay, what is the thermodynamics equivalent analog for this? So that is the macroscopic way of looking at the same thing. So for the macroscopic way, I will simply say, oh, I have 56 students, and the average of the score is, I don't know, 65%. Okay, so this one allows you to have some feeling about this class of the student too, right? So if For example, if you want to evaluate the teaching effectiveness or the learning outcome, you say, this is probably not too bad, or I can do a little bit better. If I hope, if I was aiming for 80%, then I have to work harder, and so on. So this is like what we can feel about this same class of students. Okay, and somewhere in between, there's another way to look at this. So there is somewhere in between. This is very detailed, and this is less detailed, but still gives you some idea about the performance of the class. And something a little bit in less detail, but still in between, is called the distribution. Okay, and distribution is very important, which we will of course introduce. So you have all these microstates, so you can learn how to write your distribution. For example, you can just write student A. You can say there's how many students getting a particular score, right? So I can come up with some kind of histogram, and then I can have some mark in the percentage, and I can say, okay, between 10 and 20, I have this many students, and between 80 and 90, I have this many students, and then around 60 to 70, I have this many. So from here, I can also gain some knowledge about the performance of this class. Okay, so the first part of the course will develop this, and the second part of the course, the first part of the course will develop this, the thermodynamic equivalent of this. And the second part of the course, we are going to learn how to list all the microstates. And then we will realize when we have such a big number, we cannot really do that. Then we have to rely on some kind of distribution. And from here, we will be able to calculate, surely you can convince yourself that from here, I can calculate the mean. So I will be able to come up with a way to link back to the thermodynamic observation. Okay. So for thermodynamics, we need to learn some terminologies. There are some very basic, rather intuitive, but still important to clarify right from the beginning. So when we talk about thermodynamics, we need to choose a system to study. So for example, this cartoon basically tells you what is the meaning of the system. This is the part of the universe we choose to study. And everything else is called the surrounding. We have a system, for example, a gas of a volume of gas, and that can be our system. And this is a very typical thermodynamic system we want to study. And everything else that is not that volume of gas will be called the surrounding. Okay? And the separation between the system and the surrounding is called the boundary. And that is in the thermodynamic part, this is kind of simple. So you have a different kind of boundary. And that will actually determine how complicated your system will be and how tricky it is to analyze your system. For example, if you have a rigid wall, okay, so if this boundary, sometimes we also call it wall, boundary or wall. If the boundary is rigid, think about that. If you have a rigid boundary, you cannot really change the volume and you cannot change the shape. And that means you have one channel. Now, if you can change the volume, you can actually perform work on the system. If I insist that my system is enclosed in the rigid boundary, I will not have the way to use force to perform work on this system. Okay, so this is obviously not some of the more familiar thermodynamic systems you have encountered. So one of the classic system we analyze a lot is we have a cylinder, and this cylinder is equipped with a piston. Okay, and you can move this piston up and down, and usually we put some lubricant here. That is to ensure that we do not have friction. So this is a system with a wall that is not rigid. And why do we want that? Because we want to have a system that we can discuss how to perform work on the system. Okay, so that is one of the example we are going to talk about. And still, you have this piston here. And you also need to discuss other properties. For example, can you allow heat to enter your system? Is it allowed? So if heat can enter the system, this wall is called adiabatic. This wall is called diathermic. So if heat is not allowed to enter the system, suppose you are able to enclose everything and thermally isolate your thermodynamic system from the outside world, you have an adiabatic system. Okay, so these are some very standard boundaries that we can cook up. Another thing you will have is, do you allow the particle exchange? So do you allow your gas particle to escape to the surrounding? If so, this boundary is called permeable. Okay, so if you have a system which is enclosed by the adiabatic boundary, so if you have an adiabatic boundary everywhere, you cannot really inject heat to the system. This is, for example, if you have a thermal bottle, that is kind of a good approximation, because there you have a volume of water. Your water is here, and then you will have a vacuum in between. All right, so this is a vacuum, and this wall, to a good approximation, at least for a short time scale, you do not allow heat to enter, and therefore you can keep your hot water hot, you can keep your cold drinks cold for a long time, and this is called thermal isolation. And otherwise, if you allowed the heat to flow, this is called thermal contact. For example, a good example of this would be a thermometer. If you put the thermometer on your forehead, and this is in thermal contact, and then when the heat stops flowing, you will reach thermal equilibrium. Okay, and we will have to for this course, we even have to talk about the notion of thermal contact later. How do you define the temperature? Okay, this is something that requires definition. Okay, depending on whether you allow the heat flow or the particle flow, your system will have different names. So an open system, you allow exchange of particle, you allow the exchange of energy as well. And a closed system, you do not allow the exchange of particle, but you allow the exchange of energy. So people sometimes get confused between these two. And the isolated system basically means isolated, which means if I'm outside in the surrounding, I do not know about this system. So this is, of course, very this is an idealization. So a truly isolated system, if you have an isolated system, you don't even know it's there. Okay, but for thermodynamics, we need to talk about this. Okay, so this might look very trivial. Indeed, it's not that difficult, but it's rather important. I will tell you why now. Okay. So I'm going to draw this table. Sorry, a little bit here. Okay, if you have an isolated system, what are the fixed parameter? So you have the number of particle, n is the number of particle, will be fixed. Volume will be fixed too, because if volume is not fixed, you can exchange energy by doing work. Okay, now I do not allow the volume to change. So I cannot perform work on the system. And from first law, which you will learn properly, the internal energy will also be fixed. Okay, so these are the fixed parameter. Okay, and then if you have a closed system, what happens? You do not allow the exchange of particle, so n is fixed, but the other can change because you can exchange an energy. I didn't say how to exchange an energy. Okay, but you can allow the exchange of energy by doing work, and in that case, the internal energy can be varied as well. And then open system, basically, you don't have anything fixed here. Okay, so why do we care about this? So maybe this is for the advantage of those students who have taken the 4,000 level statistical mechanics. Okay, well, you might already smell this. So if you have an open system, when you talk about the ensemble, so in statistical physics, you talk about different ensemble. Open system, just for your reference, don't worry too much, okay? At least you should know the name. This is called the grand canonical ensemble. Okay, that is why I feel that some thermodynamics is important. At least you develop a lot of things before you talk about ensemble. And if you have a closed system, this is a canonical ensemble. And an isolated system, this is called micro canonical ensemble. Okay, so for us, we are going to we are not going to talk about different ensemble. So the ensemble theory is not part of this course. So when we develop statistical physics, we have to choose one. So we are going to choose the microcanonical ensemble to develop our statistical physics later. Okay, what are the examples here? The example of isolated system, let's change color. This color is nice, I like this one. Okay, what is an open system? This is very easy. For example, a cup of coffee placed on the table. So this is open, right? Because your liquid can evaporate, so it can disappear, right? So there's not necessarily the conservation of the particle. Okay, so the example would be a cup of coffee. Cup of coffee. Okay, what is a closed system? This is again a lot. A closed system. This is kind of easy. So you can take the gas. This is a closed system actually. This one. This is a closed system. Okay, so gas in a cylinder. Gas in a cylinder. But there's not enough gas in the cylinder equipped with a piston. Equipped with a movable piston. Movable piston. Okay, so this is a closed system. My particle cannot escape. But I can do work. I can take the entire cylinder and take a hairdryer and can hit the wall. So this is possible to exchange energy. And this one will be a gas in a insulated. This one, actually, I already drew this here. If I can have an idealization like this, I have a rigid bottle, and I have I cannot allow opening, so that will be a isolated system. So this is gas in insulated rigid chamber. Okay, so at least this is something that will be useful for some of you. Okay, so when we talk about dynamics, classical dynamics, when you learn about classical dynamics, you learn about all kind of quantities, all kind of variables you need. So there you talk about, for example, the length, the mass, the time, and it's important to ask what are the variables in thermodynamics. So when you have a thermodynamics, how do you describe the thermodynamic system? How do you describe the process? How do you describe a change of a thermodynamic state from state A to state B? What are the variables here? Okay, so again, a good way to think about this is to think about that piston cylinder again. The piston cylinder, what do we want? We want to talk about the temperature of the system, right? And that is key, right? Otherwise, if it doesn't involve temperature, then then thermodynamics doesn't play a key role here. Okay, we want to know about the temperature of the system. We want to know about the volume. We want to know about the volume. We want to know about the pressure, and so on. Okay, so these are the examples of thermodynamics variables. And keep in mind, we are not talking about anything microscopic here. These are the macroscopic things that you can measure without looking at the system at the microscopic level. You don't need to talk about the constituent of this gas particle, right? When you learn about kinetic theory of gases, your starting point is different. You look at the individual particle. You talk about the kinetic part, right? They move, all right? So this is the dynamic part of this sample. But here we are not concerned with that. We don't talk about how the particle hit the wall and how do they reflect, how do they exert pressure on the wall. No, we don't talk about something like this. We talk about how much force you need to balance your system so you have an equilibrium, right? So when the piston doesn't move, you can, if you know the area of the piston, you'll be able to talk about the pressure of the entire volume, right? So of course, the entire volume is the entire volume. This is something we know how to deal with. Okay, another thing, we can also talk about the internal energy, the density, and some thermodynamic functions later. For example, Gibbs energy, Helmholtz free energy, Helmholtz function, and all these are good thermodynamic variables. Okay, because they are very important, we need to learn how to deal with them. Okay, how are you doing? Do you have questions? Tired? We can have a short break, okay? And I will, if we take a few minutes break, let's say 6 minutes, and we will come back at 12:40, and then I will continue from there. Okay, so I propose a break until 12:40. And meanwhile, I will pause the video and I will also take questions. Okay? Okay, welcome back. Okay, so before the break, we were talking about thermodynamic variables. All right, so in thermodynamic, we will have to differentiate between several. There are some key concepts we need to get it right from the beginning. Okay, so for thermodynamic variable, we need to learn the difference between extensive and intensive variables. Okay, so here again, all these are very simple definition. We are giving all this at the beginning, but when you move through the course, you will find that sometimes if you just misunderstand a key property like this, the entire argument, the entire logical structure of the argument will just fall apart. Okay, so that's why this chapter is rather important. A lot of definition, but it would be very useful to really spend some time to read them. Okay, what is the extensive property? So the extensive property is something like this. If you take a system A, let's say you take the same system, you chop it into two. If a thermodynamic variable is also scaled with the system size, and there will be an extensive variable. Okay, so if you take a system, let's say you take a system of a gas particle, and you have some, you can describe this system by all these variables. Okay, now imagine you have an imaginary partition here. And now you're asking yourself, now after you partition it into system left, system right, what happens to all these parameters? What happens to all these variables? So clearly the volume will become half, right? Originally, if we have V for the entire volume, this will be V over 2. Okay, so those variables that change with the system size is extensive. Okay, so here volume is 1. Okay, and obviously you don't have the same thing with temperature, right? If you take the temperature, the whole system has the temperature is in thermal equilibrium at temperature T. If you chop it into 2 and the temperature drops by a factor of 2, that would be very scary. You won't have something like this. Okay, so those property is called intensive. Okay, so these are the example, and you can think of the rest. Okay, this is the example of extensive and intensive. So now the question for you is, if I give you an extensive variable, can you turn it into an intensive variable? So if I give you an extensive variable, so question, can you turn an extensive variable into an intensive one? Okay, so something for you to think about. Next. Now, there are many variables in thermodynamics. So this table is very interesting. So let me spend a little bit of time on this. This is from Atkins, and you can find in other books. So it turns out that when we do thermodynamics, when we do thermodynamics, we start from first law. When we write down the first law, what we need to ask ourselves is, how many ways can we perform work on the thermodynamic system? Okay, so if you have different ways to perform work on the system, you sum over all these channels, all this contribution. Okay, so that is why thermodynamics is rather powerful and general in this sense. Because look, you do not have to appeal to microscopic details. So once you spend time, let's say you spend your effort to do thermodynamics on gas or liquid or fluid by this piston cylinder system I just described, you can actually have the entire mathematical structure for the thermodynamics of a piece of wire. Okay, you just have to modify the way to perform work on the system. For example, how do you do work on your fluid? You do work by changing the pressure, because this will give you the change of volume. Okay, and you can have something similar. You can have a filament. How do you describe the work for this term? So there will be the change of the force you use to pull, the change of tension, the application of tension and the response of the length, right? The response of the wire. Okay, it turns out that this is what we call the conjugate pair. Okay, so when we write the first law, we can look at this table and see how to pick up the variables for forming the term to describe the work. For example, the fluid which we are going to use, we are going to look at the change of work due to the pressure. So I'm going to write it quite precisely, but I will justify it in the future. Okay, so we don't write PdV because we want to also include the sign convention. So there's a minus sign here. Okay, don't worry too much at this stage, but you just have to see what happens. So we are going to pick one variable from this column and the other variable from this column, and the differential change due to the change of the pressure will give you the change of volume. And the product of this is the work done on the system. Okay, and then I will also write the right notation for you and describe it later. So for this dW, I don't want to just write dW, I want to put a bar here. Okay, and that has to do with the property of this differential. This differential is not the same as this differential. You see, this is without the bar. This is the one with the bar. Okay, more to come later. Okay, so I will do my first law based on this system. But once I learn how to do it, I can change. I can mathematically, if I have only two variables like this, they are all the same. I can one day I can decide to talk about filament, wire, or the film, and in that case, I can write a work which is a work term which is similar to this. Okay, with some appropriate sign convention. That is why don't underestimate the power of looking at this piston cylinder system and enclosing a volume of gas particle or liquid particle, because that is so general, that is something you can imagine quite well. And later you can change the thermodynamic system directly to describe something you cannot easily imagine. For example, you can describe the thermodynamics of a piece of magnet, right? This is a magnetic system. Okay, so you need to you only need to change a variable in an appropriate manner. Okay, so I give you this column, and the first column has the character of a force. So this is something that drives the change, and this is the intensive component. And the extensive component is a bit like the reaction, right? What happens when you apply this force? It's like the generalized displacement. So if you want to use a very general language, and this is this line here. Okay, so this column really acts like a generalized force, and it has a character of a force, something that drive the change. And this column has the character of a displacement. What happens when the pressure suddenly change? What do I have to react to that? Okay. Later, hopefully you will begin to really appreciate why we need to distinguish between whether a given variable is intensive or extensive. Okay, this is one key aspect of the thermodynamic variable, which I really want you to take home and think about. And the second one, which is equally important, is something which we call the state variable. So there are many names for this. Some books use the word function of state, or state function. They all mean the same thing, really. So the idea is the following. If I know the state of my thermodynamic system, let's say I'm at state A, Then I can write a list of variables. They are fixed, they are unique to this state. Okay, you might think this is, of course, this is obvious. But if you think about this a little bit more, this is not obvious at all. If I know the state of the thermodynamic system, there's no guarantee that any variable I use to describe this state has to be unique to this state. Okay, so let's first talk about those that are unique. And those variables that will be determined by the states are called state variable or the function of state. Okay, so those states, the fact that once you know the state, let's say if I draw some coordinate for you, let's say PV, okay, and think about your gas, the ideal gas. So if I label this point for you, you know your V, you know your P. Okay, P1, V1. Okay, so these are functional states. It doesn't matter how I get to this point. So that is the key. If I have a variable which is not a functional state, then it really depends on how I get there. Okay, so in that case, it depends on the path to get there. Okay, so a functional state, in other words, is a variable that has no memory. It doesn't really care about how it gets to the state 1, for example. Okay, it doesn't matter how you bring it there. Once you are there, you have a well-defined volume, you have a well-defined pressure. Okay, so in my note, I actually give you some definition, a bit long, you can look at it yourself, but what I really like is this one, a state variable. And I also think this is a very, very profound way of saying this. So this is what I really like. If I have a state variable, that state variable has no memory. It doesn't care about the path of getting there. Okay, another more formal definition is given in the note. I will read it for you, but it's easily found there. So if I have a quantity f, which is a state variable, and this is only true if and only if the change delta f depends only on the initial and final states, not on the path. Okay, let me I don't copy, but let me write this again. If f is a state variable, then delta f only depends on the endpoints. It doesn't matter how I get from A to B. Okay, so delta f means suppose my thermodynamic system is changing from state A to state B. I don't care how I draw the path between A and B. I only care about the endpoints, and that will allow me to calculate delta f. Okay, so if you have something like this, then f is a state variable. Okay, this I cannot overemphasize this. This is very important, very, very important. Okay, let me give you some example of the state variable. So state variable, for example, state variable, pressure, volume, pressure, volume. These are state variable. If we just, again, try to visualize things, try to make sense of all this using the piston cylinder system, that is the best way to learn this. These are state variable. Okay, so for my piston cylinder system, what are not state variable? Okay, I will tell you the answer. Work and heat are not state variable. Okay, so this really depends on the path, not just the endpoints. How do you go from A to B? Okay, and if we want to make progress, now we have to begin to think about how to incorporate this information here, this definition here. So we talk about delta F. But if the endpoints are very tiny, which is very likely when we talk about thermodynamics, particularly if we want to talk about thermodynamic equilibrium, we don't want to displace our system too far away from the equilibrium state. Okay, so there will be the need to have a machinery to discuss very small changes. Okay, and that is when you need to use differential. Okay, so differential of F. For example, I'm going to change to lowercase again. This is how we discuss the change. Okay, but it's okay to write this. So even for if F is not a state variable, we can write something like this. But you will very soon realize this kind of differential is not the differential you learned before. Okay, so that's why we put a bar here. And that explains why in a few slides ago, I put a bar here. Okay, because work is not a state variable, and therefore the differential, I better differentiate the differential of a state variable from that of a non-state variable. Okay, so if you have a state variable, this will be df. Okay, if your variable is not a state variable, it's not a function of state, I put a bar to denote the differential. Okay, so if you have a bar, if you have df, the usual one, this differential is called the exact differential. Or some book say use a different terminology. They say this is the proper differential. Okay, so if you have d bar, and this is inexact or improper. Okay, so unfortunately or fortunately, now this brings me to first law. I can give you some a preview of the first law. How do we write first law? We have an entire chapter on first law, but our first law looks like this. At the very beginning, right, if we want to develop first law, we write it like this: d bar q plus d bar w. That is rather annoying, don't you think? Look, on the left-hand side, you have something which is a perfect differential. And that is convenient. If you know the states, state A, state B, you know the change of the internal energy. This is the internal energy. But unfortunately, first law basically tells you to form the first law, you need to learn how to perform work on the system and how to add heat to the system. And these two both depends on the path. And that is very inconvenient. To do the calculation, I need more information than just knowing the two states. I need to know the entire path in order to calculate this. And therefore, this is one of the goals of thermodynamics, is to try to rewrite the first law in terms of exact differential. So we don't like dq. We want to be able to turn this into a exact differential. We don't really like dw. We like to turn it into an exact differential. Okay, and this you already know how, because I gave you the answer, right? This is how. And dv is an exact differential. Right? This is very interesting. Huh? On the left, you have inexact differential. On the right, you have an exact differential, and you can put an equality in between. Another way to look at this is there a way to turn an inexact differential into an exact differential? Yes. The way you do that is to multiply by some kind of factor or divide by some kind of factor. Here you can look at dw divide by p will, or d bar w multiplied by 1 over p will turn the whole thing into an exact differential. And this multiplicative factor is called the integrating factor. Okay, and that will come later. So we know how to deal with this. And how to deal with this is a long story that will eventually lead us to second law. So what is the integrating factor to turn d bar q into an exact differential? Again, a preview is this. You will see you need to introduce the notion of entropy. Okay, so if I have a piston cylinder system, I need to find the integrating factor for d bar q. Okay, and this is this itself motivate the second law. Okay, and we are going to follow this logic. But right now, you need to understand the difference between these different notations. Okay, reversibility, this is simple, and I will let you read this yourself. This is from the note. I talk about entropy. Entropy is kind of important. The idea is sometimes you will have a system that perfectly satisfies the first law. First law, if you look at first law, what is first law? First law basically is the law about the conservation of energies. So if you take heat into account, heat and work are equivalent. If you treat them on equal footing, energy is conserved. So very often you have a system that does not contradict your first law, but when you reverse it, if you reverse a process, that process completely satisfies the first law, but it doesn't happen in nature. Okay, and why is it the case? And that is the content of the second law. So second law kind of tells you why certain processes are allowed, why certain processes, when you reverse it, is not allowed. So this reversibility is kind of at the heart of thermodynamics. Okay, so second law allows you to test. And you might heard about some grand way to say that. They say second law tells you the error of time. So why you can go from past to future, but you cannot reverse it. Okay, so that is the second law. It's simple, but please read. In particular, when we talk about the piston cylinder system, try to convince yourself that if I want to have a reversible case, although it's idealization, how do we achieve this in principle? So first, I can, if I have friction, that is not reversible, right? So if I push it, I will have some heat generated here. That will not be reversible. And what can you do to make it non-reversible? You can even lubricate the piston, so you eliminate the friction in this case, but you can also make the process non-reversible if you do it in a very cowboy way. If you apply this force very fast, let's say this is kind of daily experience, right? If you hammer it, you will create a lot of very violent processes here, and you have a sound wave coming out, and this is something you cannot extract back, right? You cannot imagine putting a speaker next to it and play the sound to the piston and then to the piston cylinder, and the piston comes back by itself. No, that is not going to happen. Another way to think about it is the following. You do this process of violently compressing this, and when you do this process, you take a video of yourself doing this, and then you rewind the video and see whether that makes sense. Okay, you play the video back from backward to see whether that makes sense. And that will tell you rather intuitively whether a process is reversible or not. Okay, and this is something you can look it up, you can read it by yourself. Okay, about 4 minutes, I will stop, but I want to begin by motivate you on this. In thermodynamics, we very often need to deal with a function of two variables. So this is a function of two variables like this. Okay, this is so common in thermodynamics. For example, if you look at ideal gas, so the common example is if I look at 1 mole of ideal gas, so what do I have? I will have PV is RT. R is the gas constant. Okay, you will say, wow, there are 3 variables, but no, because you have the equality here. Once you know 2 of them, you know the third. R is a gas constant, okay, PV and T. Okay, in this case, this is really a function of 2 variables. You can solve it for V, for example. You can make V to be the subject, move P to the other side, and V clearly is a function of 2 variables like this. Okay, and this is so common in thermodynamics. We have tons of them that we need to deal with. Okay, so we want to, this is a proper, this is sometimes called the equation of state, equation of state. Okay, and we need to learn how to manipulate this. And I will come back to this f of xy and ask ourselves what happens if I have a small change in df. Another way to say that is how can I induce a small change in this function f? Okay, and how do you do that? You actually know quite well, right? If you have 2 variables, how do you induce a change in f? First, you need to have a change in x, and you need to have some change in y. That's how you do it. And both of them will give rise to the change in f. So this is really in language term. And how do you write this mathematically? You need to learn how f react to the x component by keeping y constant. And likewise, you need to do the same for the y component. So this is a y, sorry, and keeping x constant. Okay, so this is the notion of partial derivative, where this partial derivative is really nothing too new compared with the total derivative you learned before. Okay, so what is the definition of this? Let's write it out, and then we are nearly done. So I want to look at the change in f due to the change in x. So I let my x change by a little bit, but I keep my y constant. So basically, I'm looking at this quantity. And then I look at this change. So when I have a small change in x, okay? And I want this to be very small. Okay, so this is the same definition as the total derivative. Now this equation is the starting point of many manipulation in thermodynamics. From here, you will get a lot of equations involving partial derivatives, and that is you will really see a lot. Don't worry, you will see plenty later. Okay, now if I look at this, let's look at this. I can write P as a function of V and T, but this is by choice. I don't have to make my P spatial. I can equally choose my P to be a function of V and T. Okay, so coming back to the more general notation, I can equally say I want X to be a function of F and Y. Okay, and that will give me a similar equation. So then I want to ask what gives rise to the change in X. So I simply have to write this again. So I will have dx the change in x is due to the change in f and the change in y, because now I want my x to be the subject. Okay, so I will have this equation here. So I'm going to keep y constant. Now, in my course, I use two notation. Okay, I use them without thinking. Sometimes I put a line. Sometimes if I feel I want to work harder, I put brackets. So this is what I have. Okay. But what is df? I have this df here from here. So this is something I can plug in. I can change this df. This df is the same as this. So I can plug in the whole thing here. And that will give me two important relationship, which I will work out later, but you can, we have to work it out anyway next time, but you can spend 5 minutes to work it out yourself if you want to have some fun. So by plugging this in, after a few steps, you get this relationship. This is x, f. Okay, so this is called the reciprocal theorem. It might look very trivial, but you have to learn how to get this. So this is called the reciprocal theorem. And the other one, the other relationship you get, so through this manipulation, is you get a product of three partial derivative. This one. And then this one, y and f. This is x now. This product will give you -1. So this is the famous reciprocity. So this is reciprocal, and this is reciprocity theorem. Don't forget these two, and then make sure you know them really by heart. Something you can write down without deriving. Okay, so here you can see this only work exactly for three partial derivatives, and then the variable that you keep fixed has to be taking turn, right? Y, f, and x. Okay, and that will give you -1. Then these two will be used a lot for manipulating a lot of partial derivatives later. Okay, that's enough for today. Next lecture, we will pick up from here and start to do more partial derivatives, and then to ask ourselves, how can we tell whether a particular function is a function of states? Do we have a way to test whether a function is a function of states? What happens to the differential? What happens to the exact differential? And what happens to the inexact differential? And what do that mean? Okay. All right. Thank you very much.